Okay, let's talk about roots. So remember, roots are the same thing as zeros, which are very often the same thing as x-intercepts of a graph. They are the solutions to the equation if you replace the y's with 0. All of those things mean the same thing. Now, let's take a look here at these three equations. Very similar. They're all x squared, x squared, x squared, so all quadratics. But they have different constants, right? A -2, a +0, and a +2. Those end up mattering quite a bit. Let's take a look at what happens. In this first case, what I see is there are going to be two solutions here. I see those as x-intercepts on the graph. And since the graph goes straight through at those two x-intercepts, they each have a multiplicity of 1. Now, if I want to pinpoint them to see exactly what they are, take the equation, put a 0 in for the y, and then solve the equation. Add the 2 over, do a square root. X is plus and minus square root of 2. So about plus and minus 1.4, which, sure enough, looks to be where those two solutions are. So here's how I'm going to describe these solutions. Now that we know there are numbers that are not real, these imaginary numbers, the complex numbers, I'm going to classify these as being two real roots. So two real roots means there are two x-intercepts. There are two real numbers that make y 0 when you put them in for the x. Let's take a look at equation number 2. Here, I have a graph that comes down and just touches the x-axis at 0 and then bounces back up. That's what a root with an even multiplicity looks like. So in this case, it's going to be a double root. Let's see how that works. So if I've got 0 equals x squared, well, the only way this happens is if x is 0. Because that factor of x shows up twice, 0 is the solution 2 times. So I'm going to say here there is one real root with a multiplicity of 2. So very technically speaking, there's still two answers. It's 0 and then 0 again. So this first case had two solutions, plus and minus root 2. This one had two solutions, 0 and 0 again. As we look at this one, well, this one doesn't cross the x-axis. That doesn't mean there aren't roots. It just means those roots are not real numbers. To find those roots, let's do the same thing we've done here in these other cases. Put a 0 in where we see the y. That's equal to x squared plus 2. So subtract the 2. Do a square root. And what I'm going to see is x equals plus and minus. If you square root a negative, you get this I involved. So this still has two solutions, two roots. It's just that both of them are imaginary. So this one has two, and I'm going to call it a complex root. So two complex roots. Now, here's what I want you to take away. All three of these equations had two roots. Here it was two different real numbers. Here it was the same real number twice. Here it was two complex numbers. Complex because it's got this I involved because we had to square root a negative. Let's just bear that in mind as evidence. Let's take a look here at another set of cases. I'd like you to do a quick pause and come up with the three roots of this equation. Did you find them? Looks to me like we've got one here at -1, another at 0, and another at 1. And sure enough, if you substitute any of those three numbers in for the x's, you do get a 0 out for the y's. So this particular equation has three real roots. As we take a look at this second one, I can see that there's a real root right here. By looking at the graph, I see that x-intercept. Now I notice that it, again, goes straight through the graph. So it's a 0 with a multiplicity of 1. So I've got one real root, and that occurs at x equals 0. The question is, are there others? For this, we're going to have to trust our algebra skills a little bit. So if I do 0 equals x to the third plus x, let's do some factoring. These have a GCF involved. There's a factor of x in both of those. So I can make it x times x squared plus 1. Okay, here, that's that root that we already found. X equals 0 is an x-intercept. It's a root. That's because if you put a 0 in for this x, you get a 0 overall. But let's focus now on this part. If x squared plus 1 is equal to 0, what numbers make that happen? Do a subtraction of 1. Do a square root. Ooh, square root of -1 is I. So it looks like I've got 2 additional roots that are imaginary. So this particular equation has the one real root where we cross the x-axis at x equals 0. But there are also 2 other complex roots, the imaginary ones, positive I and negative I. If you substitute an I into this equation, what you're going to end up with is negative I plus I, which is 0. If you substitute negative I in for the x's, you're going to get I minus I, which is again 0. Here's what I want you to take away from this. The complex numbers are sometimes needed when you're finding the roots of an equation, and roots are important. Those are the DNA of a polynomial. That's what makes it do what it does. Sometimes your roots are real, sometimes your roots are complex, and sometimes it's a mix. But what I want you to see is how many there are. Notice how all of these had 2 real roots. Here there was 1 real root twice, so 0 and 0, so 2 roots again. This had 2 complex roots. Notice that they all had a degree, a highest exponent of 2. Degree of 2, 2 roots. Let's take a look at the next one. This one had 3 roots that were all real. This had a real and 2 complex for a total of 3 roots. 3 roots, degree 3. I'm starting to see a pattern. As a matter of fact, it's one of the most important patterns there is. So here's the deal. We've seen now that there are 2 types of roots. The real ones, those show up as x-intercepts. You can see those just by looking at a graph. The complex ones are harder to see. As a matter of fact, you can't. You need to be able to solve for those using your algebraic skills. But put this together into what's called the fundamental theorem of algebra. It turns out that whatever the degree of your polynomial is, the highest variable exponent, that's how many complex roots you have. Now here, complex includes real. So we're just saying all the roots together, the real and the imaginary and the complex, all in one, the total of those roots is the same as the degree of the polynomial. So let's take a look here. This equation, I'm not asking you to solve it. I simply want you to figure out how many roots there are. It's really as simple as this. Take a look at your exponents, find the biggest one. That's how many roots there are. Some of them might be real, some imaginary, but there's going to be that many altogether. Let's take a look at the next one. Don't overcomplicate. Taking a look at my exponents, the biggest one is 5. This one has 5 roots. Now, it could be that some are real and some are imaginary. It could be that some are multiplicity roots, like maybe one shows up more than once, but if you add them all up, if you count them all, there's going to be 5 of them in the end. And then lastly here, highest variable exponent is 4. This polynomial has 4 roots altogether. Now, what type they are and how many of them show up more than once, that's a little trickier. But if you just want to know how many there are, simply look at your highest variable exponent.